Good afternoon, everyone. We're very excited to have you with us for our webinar. I'm your host, Kimberly Eng, Latent AI's Marketing and Operations Manager, and I have the privilege of introducing you to Latent AI and our speaker, Jan Ernst. For those of you that don't know us yet, Latent AI is a venture-backed startup focused on AI success by creating the processes necessary to deliver optimized and secured models at scale. Whether you're a seasoned AI professional or just stepping into the realm of AI, this webinar promises valuable insights and innovative solutions on how to reduce time to market and significantly lessen the learning curve for design exploration and optimization. I'd like to welcome our speaker, Jan Ernst, our Director of Artificial Intelligence. With over 3 years at Latent AI, Jan has been instrumental in shaping the company's vision and mission. Before joining us, Jan brings over 15 years of experience in industrial R&D, where he was bringing innovative products to life across sectors like mobility, energy, and manufacturing. Most recently, he served as principal scientist at Siemens Research. Thank you for joining us, Jan.
Thank you, Kim, for the introduction. Welcome, everyone. Thank you again for taking the time to tune in. Today, I'll be talking about LEIP recipes, a game changer for achieving faster results and better optimization in the machine learning world with less time spent and less effort wasted. LEIP recipes are part of our ML application framework and come with all the tools you need from training data to deployment. I'll start by laying out a perspective on the ML model lifecycle, talk about challenges in the design process, and then introduce LEIP recipes and how they can dramatically improve your ML results. Before I go into what LEIP recipes are all about, let me summarize some of the benefits you get with them. Let's start with an example ML system task. Let's say you want to build analytics for a drone that can detect vehicles in real time from a top-down view. In this case, as an ML scientist with LEIP recipes, you'll get quick starting points on new data to explore what kind of performance and accuracy you can achieve. As an ML engineer, you'll get rapid prototyping, allowing you to focus your engineering effort on value creation instead of fudging engineering details. As a program manager, you'll be able to get your systems from feasibility in the lab into your product much quicker. As a system integrator, you'll have better trust and oversight over integration and component qualification during the product lifecycle. As a product manager, you'll be able to improve your time to market. Finally, as a field engineer, you can get powerful but guardrail templates to adapt a model from the lab into the field. Before I dive in to tell you about recipes, it'd be great to get a readout from you guys which role describes you best. If you can, please post this in the chat. So, to motivate a bit how we are thinking about LEIP recipes, let's start with a picture of a typical ML pipeline from data to deployment in the field or product. That doesn't mean that this is the only picture, but it helps to visualize some common pitfalls and how you can do better with LEIP recipes. Starting from data, I likely have some understanding of the constraints I may have, such as a lack of data, limitations of the inference hardware, requirements on power, latency, and accuracy, as well as timelines to get the system from feasibility in the lab to prototype to production. In our running example, you could have a certain time interval for real-time processing allocated, for instance 5 milliseconds for the video analytics. This is a system design variable. Generally, you'll have somewhat of a sequential pipeline with steps around data engineering, model design and optimization, system integration, and finally deployment. At each of these steps, you have to make design choices from suitable options. For instance, what ML model to use or what hardware to target for training and inference. This can get complicated very quickly. More likely than not, you have silos along the way, where everyone is happily throwing the results over the wall to the next guy to deal with it, and they won't take it back. What you get is a waterfall process that is one way and sequential. This makes it fundamentally hard to make decisions locally in a holistic manner, as you lack the insight into the other steps around you. If you're upstream, you don't know how your design decisions influence next steps. A typical example of this is your lab building a model that makes them happy. You'll hear them say, "Yay, we solved the problem. Accuracy of the model is great." But then you go on, put it in the product, and it turns out to be too slow, more than the 5 milliseconds that you had allocated. It may be also too big, where you're running out of memory on a particular embedded hardware. Does this mean that you should change the inference hardware to a more powerful alternative? Go into the cloud? Could you not go back to find a more suitable model for the specified hardware? Perhaps you just need a minor delta in performance to make it work as is. All of these are real-world, typical events that relate back to design decisions. In a waterfall model, they tend to suffer from the inability to go back and forth along the pipeline smoothly. Another example is if your inference hardware changes during productization or later product updates, because better hardware has become cheaper. That's how it goes. Do you go back to the lab and have them restart on an entirely different hardware? This could be a year or more later. How do you even restart a design updated in a situation like this? How do you avoid having to restart things from scratch? Wouldn't it be cool for you to focus on your domain, making the best design decisions without worrying too much what comes before and what comes after? This is difficult to do in practice, particularly if you suffer from process silos. Let's look at an interesting example. Earlier we said, it is an issue if the model turns out to be too slow for production. But really, an even more insidious and less obvious problem is if the model is too fast. What does it even mean? Our running example with real-time requirements gives me a time envelope for processing of, I think we said, 5 milliseconds for the inference. Then, if my model from the lab comes in at 3 milliseconds, I already know that I can do better. I'm basically wasting 2 milliseconds that I could use for a more powerful model. It'd be great if the integration could go back to the lab and say, "Hey guys, here is 2 more milliseconds. How much better can you do?" And then you don't worry about it anymore, even if hardware changes later. How can you improve this interplay of different silos, perspectives, and responsibilities? How do you make design decisions at the right time and right place? This is where LEIP recipes come in. In a nutshell, LEIP recipes allow you to describe system aspects from data to deployment in a semantically meaningful way, where everyone then draws from the same source of truth about the design. As a result, decisions that are made upstream can be reverted more easily once downstream trouble starts, and similarly, downstream insight can be used to revert early design decisions with less friction. LEIP recipes transform a piecemeal ML design into an agile design space exploration process. Instead of having to make opportunistic design choices, you can focus on modeling and exploring what is important to you. Instead of saying, "Hey, let's use this or that model because everyone does it, or it's the latest academic paper," you can confidently say, "Let's use this model because it fits our design requirements best, and we can replace it effortlessly once newer technology becomes available." Instead of running into various incompatibilities along the way in terms of size, optimization, trade-offs, you can rely on a semantically meaningful and guardrailed design process that not only gives you powerful abstractions from individual code implementations, but also well-qualified starting points for various system choices. Instead of saying, "I'm already vested in my model code base and training regimen, there is no way that I can go back and revise any of this," you can say, "I'm comfortable to make quick design decisions now, even with limited insight in what's to come, because I know I can revert them later if requirements change or new technology becomes available somewhere along the pipeline." This design exploration of alternatives is driven by empirical data across the pipeline and your project history, and, importantly, it is amenable to automation. I'll show a couple of really cool things there in a minute. So just what are recipes? Recipes essentially are a tree-like description of all components of an ML system in text parsable form. They capture how to ingest data, how to pre-process data, how to train, how to optimize, how to evaluate, how to prepare for deployment, and so on. They are modular, composable, shareable, and reproducible by design, even over longer periods of time. They come with semantic annotations that allow you to abstract away a lot of really irrelevant details in the system design, such as what particular model should I choose, what backbone should I choose, and lets you focus on more meaningful questions, such as what design alternatives fit into my hardware envelope. Recipes also have guardrails in the form of a constraint system that keeps you from making utterly inconsistent choices based on long-range constraints. A constraint, for instance, could be, if you want to start with a pre-trained backbone, make sure that your data normalization is consistent with how the backbone was pre-trained. Or certain optimizations, such as 4-bit quantization and lower, may not work well with particular model architectures like NanoDet. I'll admit, though, that we do provide a big old red override button that you can push if you really want to stray from the path. To give a quick taste of how powerful the Recipe Designer API is, I'll go through a couple of brief examples. Here you see the Recipe Designer API, in this case via a Jupyter notebook, hopefully familiar to a lot of you. In this example, we are changing the model family for an object detection model to YOLO V8. If you look at the first line on top, see how I can do this with one line of code, just saying my model should be something like YOLO V8. Then we can query what backbones are available for this particular family. You can see there is a bunch of options: small, medium, large, nano, extra large, right? Finally, we set the actual backbone to our desired value. Again, one line of code, done. The Recipe Designer API makes sure that any such choice is consistent and does not violate any constraints that may be there in other parts of the system. In the bottom example, we can do the same with another detector family, in this case NanoDet. You'll see a bunch of different backbones there as well. Note how the code between the two examples is the same, although the underlying code base and implementation may be dramatically different. At this point, we don't have to care. All we care is that there is a model and there is a backbone. And this exact aspect is a superpower in system modeling and performance quantization, which I'll demonstrate in a minute. But first, another example of the Recipe Designer API. The top shows how powerful the programmatic design process is. It has an outer for loop that iterates over all model families and an inner loop that iterates over all model-specific backbones. In 5 lines of code, I can cycle through all my available model families and all the individual backbones. This is easily a couple of hundred combinations depending on the domain. Note that the constraint system will make sure that only choices that are compatible with the rest of the system are returned. So, if I'm looking here at object detection data, I'll get a bunch of object detection models and backbones. If I look at image segmentation data, I'll get a bunch of image segmentation models and so on. Importantly, the code remains the same, giving powerful programmatic capability to automatic system design and exploration. The lower example illustrates the composability of LEIP recipes. You can take system components from various sources and exchange them, as long as they are semantically compatible. In this example, we are composing a recipe by taking various subcomponents from reference recipes, such as the model, data, and parts of the training regimen. Again, the constraint system will sound the alarm if components are not compatible. For instance, your optimization may include image mosaicing for object detection. If you like and share what you've designed there and someone else tries to apply your part of this recipe to natural language translation, it'll throw a whole bunch of roadblocks in your way first. So, how do we really enable efficient design space exploration? In a sense, LEIP recipes define the space of possible design alternatives. This space could be restricted to a particular task like object detection or cover more general spaces with multiple modalities and the like. The details here don't matter. What matters is that the system design is done in a programmatic fashion with a Python API, so you can immediately access the space with automation. Let me demonstrate a cool thing we've built on this idea. Similarly to how the recipe space defines the set of alternatives for your design, you could ask, from all the alternatives that work, which ones actually work well, given some notion of data and annotation distribution. To this end, we've built the recipe miner, a scalable engine that has access to a set of compute nodes and inference hardware such as various CPUs, GPUs, embedded accelerators, and so on. Given some dataset and objective, the recipe miner happily chugs along 24/7 and samples the recipe space to gather performance metrics. How well does it train? How fast does it train? How sensitive is it to the specifics of the data? How well does it optimize for inference? How fast does it run on various devices? How much power does it use during inference? Building a database of this and gathering empirical evidence with semantic annotations gives you tremendous predictive power to make better design decisions. To illustrate this, let me show you a peek into the mined recipe space. For this, I have to change the visualization quickly. All right, here we go. So, what you see here is a peek into the database. This is conditioned on some notion of the data, object detection in this case, and target hardware, which I chose ahead of time. For a different choice of data, target hardware, you would get a different table. The number of experiments here is in the tens of millions, so this is a sliver of the whole database. You could chop this in various other ways. For instance, a common problem is that I don't have a lot of data, at least early on in the design process. I could kickstart my development by selecting a space of recipes initially that trains well on low amounts of data. You get a recipe distribution that naturally favors scarce data optimizations, such as heavier augmentation, image mosaicing, and mix-ups for vision, different learning rate scheduling, smaller models, etc. Each row here is a particular recipe that describes all choices from data ingest to deployment. Each row can be a starting point for your data, and applying any such recipe to your data is a couple of lines in Python. Evaluating multiple recipes is just a for loop. Each recipe could contain hundreds of parameters and performance metrics. The columns show some of them, such as model, family, and backbone, as well as a set of relative and absolute performance metrics. Let's look at the accuracy here. You'll notice 100% for the top recipe. This does not mean that the recipe achieved 100% accuracy for the task, but that given your query, it is relatively the best performing recipe in terms of task accuracy, normalized to 100%. The table is currently sorted by the relative task accuracy. You'll notice other relative metrics, such as how long it takes to train, as well as the absolute inference time on device in milliseconds and the model size in megabytes. Without such a mined recipe space, one tends to start the design with, what is the most powerful model? Or what is the biggest model that still fits in memory? Or worse, what is everyone else using? At that point, you're already in a suboptimal design space, and you're starting to build up vested interest in your opportunistic choices that is hard to recover from later. Instead, now I can say, I get that my most accurate model is a YOLO v5, but let's say I'm willing to sacrifice 5% of my task accuracy. Can I get something faster? Turns out you can. Let's look at this guy here. Rec 644, recipe 644. It's about 5%, a bit more than 5% off relatively in accuracy. But in terms of inference time on device, it is about 5 times faster. Compare 65 milliseconds to 355 milliseconds. Similarly, just to get the first model out of the lab, I may choose a recipe that trains fast. Let's resort the table by training time. There you see a couple of recipes that train relatively faster, 2 to 3 times faster compared to the model with best accuracy, while performing only about 6% worse relatively. Although perhaps not the best task accuracy at first, this would allow you to break the waterfall and get a draft model out quickly so that downstream teams can work on the next steps in integration. while the lab continues to improve the desired speed and accuracy trade-offs. Once they find a better recipe, they have the guarantee that it'll integrate downstream just as well as the quickly trained draft model. As another example, I may wonder what performance could I fit into a particular time envelope on this hardware. Let's say I have at most 100 milliseconds for inference. So I'm restricting the models to the ones that are faster than 100 milliseconds. And then I'm again resorting by accuracy. So there you go. There is a particular efficient DET model that has the best relative accuracy just under 100 milliseconds. I could also ask what is the best model to fit into 500 megabytes of inference memory. So let me remove the speed requirement and add smaller than 500 megabytes inference and sort by training. Again, you get a bunch of options. Note how in all of this, we've never worried about what the specific recipe is. For instance, what model, what backbone, what learning rate, training and post-training optimizations, etc. But just how well it works empirically on reference data before we even train the first model. Naturally, all of this is conditioned on specific data. So it's unreasonable to expect that the relative metrics will be exactly the same for your data. However, they are well-qualified starting points that dramatically shorten the initial explorative stage of getting reasonable results while allowing downstream development to kick off right away. LEIP recipes are designed for the ML novice and the ML expert alike. They provide ease of use if you don't care about the specifics, but they are not in the way of your ML expert to dig in and eke out the last bits of performance, just as they would do manually without recipes. Let me switch back to the slides quickly. Now that we've explored how you can rethink your ML design process with LEIP recipes, let's go back to the code to experience how little code you need to train them on your data. Here we see an example of setting up your data. We are assuming the common MS Coco format. With a recipe designer helper function, here in this case called make Coco data, this is only one line. We support a bunch of common data input formats. Then you set up the database of recipes with your API key, which gives you access to the set of pre-qualified well-working recipes, similar to what I just showed you in the table. This has the notion of golden recipes here, because they work well. Then you can query, load, and inspect their empirical stats, such as how well do they train in relation to each other and what the inference time on hardware is, the same thing that I just showed in the table. Here we are showing the top 6 best performing alternatives. You can see the same models as the table just now. There was a bunch of YOLO V8, V5, a couple of efficient DET. If you'd query for recipes that run fast instead, or any other trade-off that is meaningful to you, like model size, you'll discover more, and maybe different models, such as NanoDET and others. From there on out, it's literally 3 lines of code to plug in your data into each of the top 6 recipes and train them. We have our loop over the recipes, then putting in your data set, again with a small helper function based on the recipe designer API. Finally, you can hit the train button. The recipe design already includes how to train, for instance, use of GPUs, TPUs, distributed training, and so on. This is important, as you may want to look at recipes that are reasonably trainable on your training hardware at first, before you scale up the training. Beyond just an ML factory, this is an ML factory on steroids. So, if I run the above, what will I get? Recipes are compatible with a wide range of supplemental ML tooling. Here, for instance, you see experiment tracking and weights and biases. Capabilities like logging and tracking are again already captured in the recipe design, and adding tracking via a supported backend is no more than a couple of lines of simple Python code via the recipe designer API. The recipes themselves are compact, between 5 to 15 kilobyte, depending on the complexity of the recipe. They can be serialized and shared without reference to anything else except the LEIP application framework and SDK. What that means is that you can design your system with all the goodies we've seen so far, and all you need to keep or share is the recipe, and certainly your data, or a unique reference to it. If you enable experiment tracking with any of the tracking backends, the recipe will automatically be uploaded in addition to all the other relevant data you may want to see. You can send a recipe via email or store it in a database, and anyone who has a compatible version of the LEIP SDK and application framework will be able to reproduce your exact system and be able to draw from the same source of truth about the system design. This is a very powerful mechanism to build insight over time. For instance, as you develop various ML-based products over time, at some point you can start asking, for my particular domain, what has worked well so far? What has not worked well? As you have access to the semantics of previous recipes, even over longer periods of time, you can easily explore historical correlations of good performance in your domain with model choice, resolution, sequence length, and so on. By virtue of the recipe semantics, you can do this across a wide range of model and hardware choices without worrying about the implementation details for each design alternative. To add a final piece, with the LEIP platform, you're not only getting a database of well-qualified recipes, but also an SDK that lets you execute actions such as training and post-training optimization, compilation, and deployment, all controlled by a common semantic recipe design. Besides various training-aware and post-training optimizations such as compression and quantization, it comes with a bunch of cool features such as model watermarking for security and protection of intellectual property. As a final golden nugget to tease the power of LEIP recipes, a recipe prescribes all components of an ML system, so one can package it up and deliver it essentially as a template into the field. Your lab could produce not only a best model, but bundle it with a recipe that is tailor-made for a guardrailed update process in the field. For instance, if you're worried that your data in the lab is a bit off from what you'll encounter in the field, you could package a recipe that allows a specific, well-defined, one-button fine-tuning operation on additional data that may come during deployment. As all aspects of the process are modeled in the recipe already, the lab can be confident that the field personnel performs the right training regimen, including limitations of training hardware you may have in the field. And the field personnel can gain the power of an ML expert without having the full expertise themselves. Let me talk about some anecdotal evidence to the power of LEIP recipes. One of our latest products at Latent AI are pre-made models for various use cases, such as vehicle detection from various viewpoints that come in a variety of performance trade-offs and are ready to run on several hardware platforms out of the box. We tasked ML experts to build and optimize these by hand and then compare it to a design process based on LEIP recipes, including the use of our mined recipe database. Using the mined recipe database sped up the process of building these models by a factor of over 20, while improving accuracy compared to handcrafting by an ML expert. In addition, the use of recipes gives additional incremental historical insight for your domain into what works and what doesn't, improving explainability and interpretability of results over time. All right, I realize that this brief webinar leaves many points open. I invite you to ask any questions that may have come up, or better yet, get in touch with us for a one-on-one to learn how LEIP recipes and the application framework can confidently speed up your process from data to deployment. Thank you. All right. Hope everyone can hear me. Opening the stage for questions. I'll maybe go through in order as I see them here. Kim.
Yes, so the first one we have is the recipe mining feature sounds powerful. What's the level of expertise required to use this tool?
Okay, so you're absolutely right. It's a very powerful thing. So I think there is two parts to this. right? So first of all, with the SDK, you get the whole recipe design space. So you could start by seeing the recipe mining as basically hyperparameter search on steroids, right? Where you can use your own hyperparameter search, but extend it to all of the continuous and discrete choices that are there, automatically mapping them out in the hyperparameter search. So you can build your own mined database. I think the challenging part comes in once you put hardware into the loop. This is what we are doing with the recipe miner. As I mentioned, right, it's connected here in the lab to a whole array of edge hardware and compute nodes. And that is first for internal qualification, right? So at the moment, to onboard new hardware, you can come in and say, hey, I'm interested in this hardware. Can you run the space? And then at a later stage, basically we see how easy can we make it for yourself to do the same thing, basically replicating this full-blown end-to-end mining yourself.
Thanks, Jan. We have another question from Mark. Is this just for edge devices or does it work with the cloud?
Good question, right? So generally all our software tooling can be deployed locally on your machine, can be run in the cloud, right? It's a Docker container type deployment for the tooling itself. Meaning you can train on your own machine, you can do the optimization, compilation, right? Given minimum requirements on the machine. For training, certainly you need bigger hardware. For compilation, optimization, testing, evaluation, maybe smaller hardware. Fundamentally, we distribute all sorts of fabrics for training, for instance, in a distributed fashion. The other aspect of that question is what are the targets that we're supporting, right, for inference, right? And there we're supporting a wide array from all the way down to FPGAs, all the way up to data center GPUs, where you can specify, hey, this is my target hardware on which I want to run the inference, and then you can target that.
Nice. We have another question. The quality and kind of data can have implications on model architecture and types of models that perform well on the data. How do we identify the best recipe for previous unknown data without training, if at all possible?
That is an excellent question, right? And fundamentally, you won't be able to do that, right? Strictly speaking, from a purely academic perspective, right? Because you don't know what's in the data. Taking a more practical stance, right? What we are doing basically, right, is we are scouring through all sorts of different data, right? Looking at the statistics. Maybe there is data that is scarce, as I mentioned earlier, or data that has a lot of annotations, a lot of classes or little classes, right? So you can kind of empirically span that space. With a recipe miner, it's basically just a matter of throwing in the data and then giving it time to churn out the results. What we are also doing is cross-validating, basically, right? If you find a recipe on some data, you can ask the question, how well does it work on other data? So you're not only getting kind of the relative performance metrics, but you also get a notion of how well it may generalize beyond that exact data that you had. So that's a bit of an extra buffer of safety for your recipe. In terms of you going in practically, right, you have your data. Now, where do you start? We will provide to you sort of a baseball scorecard, right? Basically a set of flip cards that you can go through that illustrate what kind of reference data are there in the golden recipes. And then you can go and say, hey, this particular data set looks kind of close-ish in terms of the structure of the data, right? The amount of data, number of classes, whatever that may be. And then you can go in and say, this is the database aspect that I want to start from, and mix and match your recipes. That doesn't mean that you can't go to other data, right? If you feel that 2 or 3 are closed or none are closed, just go randomly. Likely you'll have reasonable starting points at least. even for your data. But again, this is kind of a practical perspective. From an academic perspective, there is no such guarantee. So all we can do is to build the empirical insight, so that we have better and better data to support, hey, it will actually work on your data over time because we've done it many times before. And this is something that is very fundamental and enabled through the automation aspect of LEIP recipes.
Okay, next question. What other tools does it work with? Can I log into different loggers used in my organizations like Neptune AI or W&B, weights and biases?
Good question, right? So there is a couple of different tools along the pipeline, right? This is a question that is more along the training side, let's say, right, for our training portfolio. The infrastructure that we are using for the training is fairly industry standard based on PyTorch Lightning. This is our main training driver. And with that and a bit of extra modules on our end, you get compatibility with a bunch of tools on the logging side, TensorBoard, what do I see here, Neptune, weights and biases, these we all cover, and a couple of more, as well as other supplemental tooling that you may need for your ML process. And it's extensible. You can add, and we can add modules that may fill some gap that you see for your domain. It would be interesting to see from you guys what the main toolings are that you use.
Okay, I think we should have time for maybe 2 or 3 more questions. The next one is, it is not uncommon to find that for custom data, the model needs to be customized to see and extract the best performance. How does this tool lend itself to manipulating the model?
Okay. So we have been trying to build the tooling and the API so that you can get started very quickly, right? You saw earlier on the slides that I showed some examples of the Recipe Designer API, which is a way to manipulate, introspect, inspect recipes in Python. I feel fairly confident that this would allow a novice user to quickly build very complex training, optimization, and deployment strategies. Now, the mined recipes are meant as starting points, right? So it's not the expectation that you run one of these and then it's the best performance for your data. So there is definitely a case where you need to go in and fiddle around with all the parameters that may be there around the model, around the training, around data augmentation, and so on. And the way that our recipe designer is built, that it's not in the way of doing this. So you still have access all the way down to the last bit in manipulating whatever you feel is necessary to get the performance.
Okay, I think we'll take one more question. Thank you for all of your great questions so far. We'll finish with, can I run your tools entirely on premise? We have an air-gapped network and security restraints.
With a bit of setup, you can do this, yes. So you need to be connected at some point just to stream all the relevant data. But from that point on, you can say, now I'm air-gapped. And you could package this as well ahead of time. So you can fundamentally deploy on an air-gapped system, right? We put extra attention to achieve the ability to be air-gapped, also because of this updating in the field aspect, right? We wanted to be able to capture use cases where I build a model in the lab, right, where I have all the connectivity and big compute cluster, and I can really build the best model. But then you go out in the field and something happens there, right? Conditions change, your context is a bit different. May not be relevant for manufacturing, but in certain domains, it's definitely happening, right? And at the moment, you don't have any recourse, right? You have to live with maybe limited performance because your conditions in the field turn out to be slightly different and you just can't update. We wanted to address that case, right? And the presumption is that in the field, you only have very small hardware and you're definitely air gapped, right? You don't want any interference. So we have the ability to template the recipes and then have certain limited and guardrailed updates, like adapting to slightly new data and doing a bit of fine tuning in the field that can be packaged from the lab. And that requires kind of this air-gapped environment in the first place.
Oh, we do have one more, and I think we have 3 more minutes. So Jan, if you think you can squeeze this in, we can
Sure.
try. Can I see the memory requirements and inference speeds on my specific deployment hardware to help me pick the model before training?
Right, exactly. As I showed in the table earlier, right? These are literally validated results. The way that it works at the moment is that you have access to our quantified recipe database, which captures a bunch of different hardware. So for each model, you fundamentally can go in and say, what is my speed on this and this hardware? This certainly presumes that you're using one of the hardwares that we've onboarded already, and we are onboarding more hardware over time. If you have a particular hardware in mind that is not covered, then certainly the best next step for you would be to get in touch with us.
All right, thank you so much, Jan, and thank you everyone for attending. I'm just going to wrap this up really quickly. If you have any follow-up questions, please contact mlops@leightonai.com. For more information in general, you can visit our website. And for those of you joining us and hearing about us for the first time, I hope we can continue our journey together, and we really look forward to you joining us in the future. Thanks, Jan, and thanks, everyone.
Thank you. Bye-bye, everyone.